All right, so let's take a minute and run through this one. So I'm going to do problems 3A and B. I will say that these are two of the most commonly missed problems at this point in the chapter. So if you struggled with these, don't worry about it. And follow along. If this makes sense, cool. If not, stop in and see me before or after school or during student support or whatever that looks like when you're watching this video. All right. So it says make a free body diagram and find the net force and the acceleration for the object in bold print. All right. So first of all, let's talk about, so we've got a 25 kilogram box, right? Okay, so before we get to the problem, let's suppose that we just had the 25 kilogram box sitting on a table, all right? So what we do is we'd go, all right, here's my 25 kilogram box. When you make a free body diagram, let's see, you always start with your force of gravity. So our force of gravity is gonna be 25 times negative 9.8, that's negative 245 newtons. Now, if the box is just sitting there, then what I know is my velocity is 0 and constant. Oh, that means my acceleration is 0. Oh, that means my net force is 0. Okay, so indirectly, what I really just did there is I used this equation to find my net force, right? Because I knew the acceleration was 0, so I know the net force is 0. All right, so now what I need to do is I need to figure out what's going on. Well, according to my drawing, the net force is not 0. Right now, I've got a net force of negative 245. So there's got to be something pushing up on this thing to prevent it from going down. And the something is the table that it's sitting on, right? Oh, so my normal force has got to be big enough to make my net force 0. So if I've got 245 down, I have to have 245 up. All right, so that's what my free body diagram looks like if the box is just sitting there on a table by itself, okay? So cool. Couple quick things about normal force. First of all, it is always perpendicular to your surface. So in this problem, here is my surface. Here's my normal force. Notice those are perpendicular. Secondly, it always points away from the surface, never into the surface, okay? So it's got to point this way, all right? Now, when you are drawing your vertical forces, your normal force should always be the last one you do, okay? Because what happens is a lot of times people make this false assumption that, like in this particular example, it is true that my normal force and gravity are equal to one another, right? I mean, except for the signs, right? That's not always true, okay? It's not always true. It happens to be true if those are the only two vertical forces and the object isn't moving up or down or accelerating up or down, okay? But as a general rule, that is not always true, okay? So please, please, please do not get in the habit of putting in your gravity and then right away putting in your normal force because they're not always equal. They are often, but not always. All right, so with that in mind, let's run through number 3A now, all right? So why don't we take this, shrink it, oh, fail. I'm gonna shrink it. Aha. All right, and let's move it over here out of the way for us. All right, so let's do part A. Part A. So we've got a 25 kilogram box at rest on a table, and then Roy lifts up on it with a force of 100 newtons. All right, so I'm going to follow my same process. Here's the box. I know that the mass is 25 kilograms. I'm going to, as I always do, start with my force of gravity. So force of gravity has not changed, right? It's just 25 times negative 9.8. That's negative 245 newtons. So that should always be your first step. Identify your mass and your force of gravity. Step 2, identify any given forces. It says Roy lifts up on it with a force of 100 newtons. So let's go ahead and put that in. Force of Roy, 100 newtons. All right. So now this is the tough part. We need to think a little bit. All right. So Roy presumably is attempting to lift the box. And so the question is, does he succeed? All right. So just because he's lifting up on it doesn't necessarily mean it moves, right? Like, check it out. Here is, this whole thing is sitting on a table, right? I'm lifting up on it, but it doesn't move, right? Because I am weak and did not exert enough force to lift the table. All right. So our question here needs to be, in this particular instance, is this 100 newtons going to be enough to lift it? Well, he's exerting a force of 100 newtons, but it weighs 245 newtons. Does it seem like that's enough? No, there's no way that this thing is going to accelerate given these circumstances, right? So it's not going to accelerate up because Roy doesn't have enough force to lift it. okay? But similarly, it can't accelerate down because there's a table in the way, right? Oh, so what this means then is my velocity, once again, is going to be constant at v equals 0, which means my acceleration is 0, which means my net force has to be 0, which means there has to be another force. Well, since he hasn't lifted it off of the table, there has to be a normal force, okay? And so now what I can do, this is probably a little bit more work than most of you need to write out, but basically what we're going to do is we're going to go, oh, well, I know that net force is my total force. So it's gravity plus Roy plus normal force, and solve for your normal force. I know the net force is 0 because Roy's force wasn't enough to lift it. I know my force of gravity is negative 245. I know my force of Roy is 100 plus some normal force. And then algebra it, and you'll get 145 newtons. All right. Now, obviously, you could have solved that without, going through this process just by thinking, oh, well, I've got 245 down. I need to have 245 up, so I need another 145. And that also works. All right. So this is my complete free body diagram here. Okay. Two common mistakes. Common mistake number one is people assume there's no normal force, in which case the box would then be accelerating down through the table, which doesn't make sense. Common mistake number two is people make the normal force equal to gravity, but then you've somehow got, you would end up with a net force upwards there, right? Because you'd have 245 and 100 up and 245 down, so you'd have a net force of 100. So then you'd have the normal force somehow lifting the box off of the table, which doesn't make sense because the normal force is coming from the table. Okay, so that is part A. I really want to say questions. You clearly don't have questions because you're watching this virtually. If you do have questions, come see me. All right. Okay, let's do part B now. All right, so I'm going to once again move this thing out of my way. All right, so now in part B, the only difference with part B is that Roy is now exerting 300 newtons. Oh, shoot, I changed the color of my previous one. All right, the only difference with part B is that Roy's force is now 300 newtons. So we're gonna have the same start that we did before. 25 kilograms, it's initially at rest on a table. Start with your force of gravity. It's gonna be negative 245 newtons. All right, that's always your step one. Step two is any given forces, which in this case is Roy's force. So go ahead and put in your force of Roy. All right, and now we kind of go through the same train of thought we went through a minute ago. Roy's trying to lift the box, right? Is 300 newtons enough to lift it? Well, right now it looks to me like Roy is beating gravity, so I think he's going to succeed in lifting it, right? Oh, well, that means he's going to lift it up off of the table, and since it's no longer touching the table can't be exerting a force on the box anymore, right? So because he has succeeded in lifting it, there is no normal force, and it's going to accelerate up at some rate that we don't know. All right. So in all of the previous examples, the idea is we knew it wasn't moving. So in these ones, we knew that our net force had to be 0 because the box wasn't moving, right? But over here, we don't know that our acceleration is 0. Okay. So I need to find another way to find my net force. So I can't use this guy because I don't know what my acceleration is. So what I'm going to do is I'm going to use the definition of net force. The definition of net force is the sum of all of my forces. So what are the forces acting on the box? Well, there's gravity, there's Roy. Because he's lifting it, there's no normal force because he's got it off the table. There's no friction because we're not trying to make it slide. There's no other people around. I think that's it. So I think our net force here, oh no, I'm running out of room. There we go. So I think our net force is going to be, let's see, gravity is negative 245. Roy is 300. Oh, so our net force is going to be 55 newtons. And now I can use this equation to find the acceleration. So algebraify that and you get acceleration is net force over mass. So we've got a net force of 55 newtons acting on the box. It's got a mass of 25 kilograms. Divide it and you get 2.2 meters per second squared. All right. So there is only a normal force if the object is physically in contact with the surface. Okay. The normal force does not necessarily have to equal the force of gravity. We'll learn later on the normal force isn't always even straight up, okay? Normal force can act in all kinds of different directions, and we'll learn that later because it depends on the direction your surface is facing. Basically, if there is a normal force, the normal force will be exactly strong enough to prevent the object from going through the surface, but not so big that it gets lifted off of the surface. Okay? All right, cool. If you have questions, holler at me. I'm around. Stop.